So welcome to Everyday Mathematics. Today we step back to the 2023 Columbia University Integration B qualifying round. And this part is part one, where we look at the 10 problems. The 10 first problems are problem 1 to 10 of that round. So this is problem number 1, problem number 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are certainly very interesting problems. Now, before we move forward to solving these problems, I would like to encourage those who haven't subscribed to our channel, please spare a minute or a second and please do subscribe to our channel. Your support will go a long way in helping us reaching our goal of getting this channel really popularized. So without much ado, we are moving forward to solving these problems. So the first problem is the indefinite integral of the product of x squared and the square root of 1 plus x to the power 6. So one thing we could do is re-express this problem as x squared times the integral of x squared times 1 plus x to the 3 squared. And why I've gone with x to the 3 is because I've seen x squared here is the derivative, at least the x term is derivative of x to the third. So I can now go ahead and say let u be equal to x cubed. And what that means is that du dx is equals to 3x squared, implying that a third of du can be used to substitute for x squared dx. And as we can see, this and that together can be substituted off. So our integral now becomes 1 plus u squared, and then dx times x squared becomes a third du, which is good. Now, one other thing we could do is now we'd go ahead and substitute for u with the trigonometrical function. I would like to use the tangent, so I could say let u be equal to the tangent of theta, such that du d theta is equal to sec squared theta, implying that we can substitute for du with sec squared theta d theta. Okay, so implying that our problem now becomes 1 over 3 integral of 1 plus u squared, which happens to be tangent squared theta, times sec squared theta d theta. So which is a third. This part here is the same as sec squared theta, square root, we get sec theta times sec squared theta d theta, which is equals to a third sec cube theta theta. Okay, so it is fascinating. We've come to a point where our problem is a third that, which can also be expressed as a third sec squared sec theta, which is a third. Sec squared theta is the same as tan squared theta plus 1. It's a third tan squared theta sec theta plus sec theta. Okay, we can now express this as a third, and we have tangent theta times the derivative of sec theta plus sec theta. We can use now integration by parts. So if we have a third, tangent theta, derivative of sec theta plus sec theta. What do we do there? We can use integration by parts, which says that if we have a product of v and a function, the derivative of function u, we have uv minus u dv. So this happens to be our u and this is our v. So we come to a third, and then we have tangent theta, sec theta, minus the integral over tangent is sec squared theta, and so times sec theta. Okay, plus the integral of sec theta is natural logarithm of sec theta plus tangent of theta, close the big bracket. So this guy here comes back to sec theta, and because so if we can express this as a third, tangent theta, sec theta minus a third plus a third log of sec theta plus tangent theta. This here is the same as I, our initial integral, right? So if we had I on the left hand side, we can now bring this onto this side. And so we have 2I is equals to a third tangent theta sec theta plus a third log of sec theta plus tangent of theta plus c. And so therefore I is 1 over 6 tangent theta sec theta plus 1 over 6 log sec theta plus tan theta plus c. Now this is 1 over 6 tangent theta square root of 1 plus tangent square theta plus 1 over 6 log square root of 1 plus theta plus tangent theta plus c. Since we said u is equals to tangent theta, our integral in terms of u, which is a third, 1 plus u squared du is equals to 1 over 6 u square root of 1 plus u squared plus 1 over 6 natural logarithm of 1 plus u squared square root plus u plus the integration constant. Now also, since we say that 1 over 3 square root of 1 plus u squared is equals to 1 over 6 u square root of 1 plus u squared plus 1 over 6 natural logarithm of 1 plus u squared square root plus u plus c. But u was set to x cubed, and therefore the integral in terms of x goes to 6 x cubed 1 plus x to the power 6 plus 1 over 6 log of square root of 1 plus 6 plus x cubed plus the integration constant. And that happens to be the answer that was required. So let's look at method 2 and how we could solve this. So the initial thing was we would express this integral as the integral of the square root of 1 plus x to the 3 squared x squared dx, and we would say let u be equal to x cubed, so that that du is equals to x squared dx. So we'd already seen this part, and so integral in the u domain becomes a third square root of 1 plus u squared du. And then here is where we'd now say let u be equal to hyperbolic sine of let's say y, such that du dy be equal to hyperbolic cosine of y, and meaning that du could be substituted off with that. So what happens here is that a third, the integral of the square root of 1 plus u squared, will be equal to a third integral square root of 1 plus the hyperbolic sine squared cos y dy. So this is a third. We get cos squared y, cos y, which is a third integral of cos y, which is a third cos squared y dy, which is also 1 over 6 cos of 2y plus 1, which now can be integrated into a sixth, a half sinh of 2y plus y plus the integration constant. Okay, so we have come to a point where we have 6 times a half hyperbolic sine of 2y plus y plus c, which is 1 over 6. We can expand this twice hyperbolic sine into a single angle, it's not really an angle, but single variable expression. And this means we have 1 over 6 cos plus y plus c. Then how can we express cos y in form of sine, hyperbolic sine? We have square root of 1 plus the square of hyperbolic sine y plus y plus c. So we had said that u was going to be equal to hyperbolic sine of y, which means that u is equals to e to the y minus e to the minus y over 2. Multiply 2 both sides, we get 2u is equals to e to the y minus e to the minus y, which means that if we multiply by e to the y on both sides, we get 2u e to the y is equals to e to the 2y minus 1, And so e to the 2y minus 2u e to the y minus 1 is equals to 0. And so e to the y using quadratic formula is 2u plus minus square root of 4u squared plus 4 divided by 2, which means that e to the y which is u plus minus u squared plus 1, but e to the y is always a positive, and so we'll choose that. Okay, and therefore y is equals to natural log of u plus the square root of y plus that. Okay, so we had gotten to a point where our integral was equal to 1 over 6 hyperbolic sine of y, 1 plus the square plus y plus c, so which is 6u 1 plus u squared plus the log of u plus 1 plus u squared plus c. But also we had said that u was equal to x cubed, so we are back to a point where the integral of x squared 1 plus x to the 6 is equals to 1 over 6 open bracket x cubed square root 1 x6 plus log x cubed plus the square root of 1 plus x to the 6 plus c. And that is our answer. So the next problem, problem number 2, is the indefinite integral of 1 over x squared minus x plus 1, which can be expressed as 1 over x minus a half squared minus a quarter plus 1, which is 1 over x minus a half squared plus 3 over 4. So we can when we see such a thing in the denominator, the quickest substitution is that, such that dx d theta is equals to root 3 over 2 sec squared theta. Apologize, I went a little bit too fast there. And so what that means is dx is equals to, or can be used to, or can be substituted with root 3 over 2 sec squared theta d theta. And that means that now 1 over x minus a half squared plus 3 over 4 is equals, in the theta domain we have 3 over 4 tan squared theta plus 3 over 4 and root 3 over 2 sec theta. So what that leads us to, since we have come to a point where we have 1 over 3 over 4 can pull the constant out, and we have 1 over so this becomes sec squared theta, so we are at a point where we have right, and this and this interact, so we're left with 1 over root 3 over 2 in the denominator, and this and that cancel, so we're left with 1 under the integration sign. So since we are left with, this means that this is, but since we had said x minus a half is root 3 over 2 tan theta, this means that 2x over 1 over root 3 is this tan theta, and so theta is arctan of 2x minus 1 over root 3. Therefore, our integral of 1 over x squared minus x plus 1 is equals to 2 over root 3 arctangent of 2x minus 1 over root 3 plus c. Right? And that's our answer. So on to problem number 3, which is the definite integral of x squared minus x minus 9 over x squared minus x minus 6, which can be expressed as x squared minus x minus 6 minus 3 over x squared minus x minus 6, which we can now divide into two separate fractions. See that these are the same, the numerator and denominator are the same, so we have 1 minus 3 over x squared minus x, right? And so we have 1 minus 3 over x squared minus 3x plus 2x minus 6. This is what amounts to this negative x, because we want to factorize that denominator. So we have 3 minus 3 over x minus 3, 2x minus 3 dx. We can now factorize that nicely. So we have integral 1 minus 3 over x plus 2, x minus 3. So this is the same as 1 minus, we can pull 3 out, and we have so we have x minus 3, and then subtract. So we have x over 2. But when you combine things, you're going to get a x plus 2 minus x minus 3, which is going to be 5. So we have to divide by 5 there. So we'll come now with x as our integrand, 3 over 5 in bracket natural log of x minus 3 minus natural log of x plus 2 plus c. And so we can actually express this as 3 over 5 natural log of x plus 2 over x minus 3 plus the integration constant. And that is our answer. So on to problem number 4, and then one thing we could do is we can see that x to the 3 comes as a derivative of x to the 4 without really factoring in the constant. So we can now express this as x to the 3 over 1 plus x to the 4 squared. And so we can also let u be equal to x to the 4, which means that du dx is equals to 4x cubed, meaning that a quarter of du can be used to substitute for x cubed dx. And so x cubed over 1 plus x to the 4, squared is the same as a quarter. Let's probably just delete this and write that a little bit better. So we have x, so we are du over 1 plus u squared. So this is a famous integral, and we know it to be which is, since u is equals to x to the 4, we can now say that x cubed over 1 plus x to the 8 is equal to a quarter arctangent x to the 4 plus c. And that is the answer. So we may want to align our equal sign here. If you are super OD about it, is our answer. So on to problem number 5, the indefinite integral of cosine of x times the 4th power of the cosecant of x. Let's just write it so that we express it in form of 1 over sine to the 4th, and we can say let u be equal to sine of x such that du dx equals to cosine of x, and so we can now substitute for cosine of x dx with du. So from here our integral becomes, since this and that becomes du, we have 1 over u to the 4th du, which when integrated is the same as 1 over 3 u to the power 3 plus c. And since u was set to sine of x, then it means that the integral of cosine of x cosec to the 4th of x is equals to negative a third sine to the 3 over x plus c, which is also negative a third cosec to the 3 or the 3rd power of x. So that happens to be our answer. As simple as that. So problem number 6, the indefinite integral of cosine of square root of x. We're going to begin by substituting for the square root of x by saying let u be equal to square root of x, and when we square both sides we have u squared equals to x, such that 2u du dx equals to 1, and therefore we can substitute for dx with 2u du. So this is important step, and therefore having our integral in the x domain can now be transformed to the u domain in the following way. we can pull 2 out and also express cosine u as the derivative of sine of u with respect to u, such that we can now employ integration by parts, where if we have an integral of the product of v and the derivative function of u, we have uv, when this is integrated, minus u dv. So using that, this is our u, means that we have u 2 times u sine of u, that's our uv, minus the integral of sine of u times the derivative of u with respect to u, which is 1. So which is 2u sine of u plus 2 cosine of u plus the integration constant. Since u was set to be that, it means that that integral is the same as 2 square root of x sine of square root of x plus 2 cosine of square root of x plus c. And that's it. So problem number 7, which is the indefinite integral of the cube of sine of x plus the cube of cosine of x. We can begin by expressing this problem as follows, right? So we have sine cube expressed as sine x times sine squared of x, cosine cube of x expressed as cosine squared times cosine squared of x, which is the same as the integral of sine of x times minus cosine squared x, and here cosine x minus 1 times sine squared of x, which is sine of x minus cosine squared of x times sine of x plus cosine of x minus sine squared cosine of x dx. So as we can see here, we can say this is sine of x minus still we can say this is plus the derivative of 1 over 3 cosine cube of x plus cosine of x minus the derivative of 1 over 3 sine cube of x. So this means that our integral becomes negative cosine x. This is integrating sine x plus a third cosine cube of x plus sine of x minus a third sine cube of x plus c. What do we get? So we say that now our integral of sine cube of x plus cosine cube of x, that integrated is the same as sine x minus cosine of x plus a third of in bracket cosine cube of x minus sine cube of x plus c. And that is the answer. Problem number 8 happens to be the indefinite integral of 1 over the tangent of x. So we can express this as 1 over 1 plus sine of x over cosine of x, which is the same as cosine of x over cosine of x plus sine of x. And we can do the following. We can multiply both the numerator and the denominator by cosine x minus sine x. So if we do that, if we do that, since we have a difference of 2 squares in the denominator, we'll get cosine x minus sine squared of x. In the numerator, we're going to have cosine squared of x minus cosine x sine x. Right? And so since we have cosine squared x minus cosine x sine x, cosine squared x minus sine squared x in the denominator, the numerator here can be expressed as a half cosine 2x plus 1 minus this can be expressed as a half sine of 2x all over. This can be expressed as cosine of 2x, right? So pulling half out, we have cosine of 2x over cosine of 2x. We have 1 over cosine of 2x, and we have minus sine 2x over cosine of 2x. So you see that cancel. So essentially we do have half times the integral of 1 plus 1 over cosine of 2x minus sine 2x over cosine 2x. So which is a half 1 plus this is secant of 2x minus the numerator is the same as plus the derivative of cosine of 2x times a half, right? So when we integrate this, we get a half of x plus a half times a half of the natural logarithm. When we integrate secant 2x, we get half of secant of secant of 2x plus the tangent of 2x plus a half times a half of the natural logarithm of cosine of 2x. Okay, so we have a half x plus a quarter of the natural logarithm of the secant of 2x plus tangent of 2x plus a quarter natural logarithm of cosine of 2x plus c. We see using the rules of logs, we have a quarter log, and now we have secant of 2x plus tangent of 2x in bracket times cosine of 2x plus c, which is a quarter of x plus a quarter So secant of 2x is same as 1 over cosine of 2x times the cosine of 2x. We get 1 plus tangent of 2x times cosine of 2x. We have sine of 2x plus c. And that is what was expected. So we can summarize our original integral, which was 1 over 1 plus tangent of x as being equal to a half of x plus a quarter of the natural logarithm of 1 plus sine of 2x plus the integration constant c. And that was the answer expected. Number 9 happens to be the indefinite integral of 1 minus cosine of x over 1 plus cosine of x. I think we're going to take the same approach as we did with problem number 8, where we rationalize the denominator by doing the difference of two squares. So what we're doing here is we're going to rewrite this problem where we have 1 minus cosine of x over 1 plus cosine of x, and then we have 1 minus cosine of x in the denominator multiplied and also the same to the numerator. So we have 1 minus twice cosine of x plus cosine squared of x over 1 minus cosine squared of x. So this is the same as 1 minus 2 cosine of x plus cosine squared of x over sine squared of x. And so a couple of things, we can re-express this as cosec squared x minus, we have 2 cotangent of x cosec of x plus cotangent squared of x. And we can even go ahead to say that this cotangent squared of x is, so if we have cosec squared of x minus twice cotangent of x times cosec of x plus cotangent squared of x. This here is the same as cosecant squared of x minus 1, so we have cosec squared of x minus 2 cotangent of x cosec of x plus cosec squared x minus 1. So this and that gel up so that we have 2 cosec squared of x minus 2 cotangent of x cosec of x minus 1. And so we know cosec squared x is negative cosec squared x is what we get when we differentiate cotangent of x. So what we're going to get here is this is 2 cotangent of x when integrated, and then this as well, this is what we get when we differentiate cosec of x. So we have twice cosec of x minus x plus c. And so our 1 minus cosine of x plus 1 plus cosine of x is equals to twice cotangent of x plus twice cosec of x minus x plus c. And that is the answer. To the last problem number 10 rather, is the indefinite integral of arc cosine squared of x And I would like to express it in a way that is easy for me to really see what's happening here. So I have big bracket and I say cosine of x squared, so that I could then go ahead and say let u be equal to cosine of x, such that cosine of u is equals to x, meaning that negative sine of u du dx would be equal to 1. So I can then say, using negative sine of u du, I can substitute off dx, right? So, and so my problem now can be expressed as u squared, because this is u, and then negative sine u du. And so I know that this negative sine u is the derivative of cosine of u, and using integration by parts, where I have b du, I get uv minus u dv. Okay, so having u squared du cosine of u, this becomes uv is u squared cosine of u minus cosine of u. Derivative of u squared is going to be 2u, right? So we have u squared cosine of u minus 2. Cosine u can be expressed as the derivative of sine of u, right? And so nesting that process, we have 2 in bracket u sine of u minus, and we're going to have sine of u. Derivative of u is going to be 1, so that's what we're going to have. And we have now u squared cosine of u minus 2u sine of u plus 2 . So sine of u integrated is negative cosine of u. So what I'll do here is I will remove that, and we'll have minus cosine of u plus c. Okay, so but u was a cosine of x, right? So if we have u squared cosine of u minus 2u sine of u minus 2 cosine of u plus c, this is u squared cosine of u minus 2u bracket 1 minus cosine squared of u minus 2 cosine of u plus c. And so cos squared of x integrated is going to be equal to, this is arc cos squared of x, and that is going to be cosine of arc cosine, so this is going to be x minus 2 arc cos of x times square root of 1 minus x squared minus 2 x plus c, which we can say, okay, let's pull really, let's rewrite it nicely in one row. We'll just say this is x arc cos squared of x minus 2 square root of 1 minus x squared times arc cos of x minus 2x plus c. And that is the answer. Okay, so without much ado, thank you so much for hanging around with us. Until next time, we pray and hope you have a nice time. If you haven't subscribed to our channel, we do encourage you to subscribe to our channel. If you like what you see, please just spare a minute and like it, but also share if you can. Until next time, à la prochaine fois.